The new APEX 2012 gives users additional control over the optical properties in this system, resulting in faster, more accurate simulations. Specifically, the Fresnel coefficient settings can now be done on an object-by-object basis. ABg and K-Correlation functions have been added to the scatter database. And finally, we've added an importance edge capability that allows for directed scatter calculations, which is critical to doing stray light analysis. Let's take a look at these new features one by one. First, remember that the Fresnel coefficient settings can be applied on a global basis through the Project Settings menu as shown here. Let's suppose, however, that I want a different setting on a particular object in the system. The way I do that is by going to the Optics Manager tree, right-clicking on that object, and choosing the Fresnel option here. For instance, in the case of a beam splitter, I might want to fix reflection and transmission independent of angle of incidence. In that case, I would choose the normal incidence approximation. Next, let's take a look at the new scatter models. These are accessed through the Scatter Model Property Manager as shown here. On the left side of the screen, we have our scatter model libraries. The list at the bottom shows predefined scatter functions that are adjustable by the user, including the new ABg and K-Correlation models. If I select on ABg and click the New button, a window appears that allows me to input the 3 ABg parameters. For a description of these parameters, the user is referred to the help file in APEX. In addition to ABg, there's also the K-Correlation model, right here. Again, if I click on the New button, this window allows the user to set the values of the 6 parameters for the K-Correlation scatter model. Details on this can also be found in APEX Help. The ABg and K-Correlation models are similar to the Harvey function and are often used to describe scatter from smooth optical surfaces. Finally, let's talk about the new importance edge feature and how the user goes about setting that up in a system such as this one. In this optical system, we've applied Lambertian scatter properties to the surface behind the lens here. If I do a ray trace using the default settings, what I'll probably see is something like this. As we can see, rays scatter in all directions in a physically realistic manner. The only problem with this is that only a small number of rays reach the detector, while a large number of rays propagate in other directions and end up not being useful for the simulation result. What we want to do here is tell the program to ignore those rays and only trace rays that eventually reach the detector. That's the role of the importance edge. There are 2 steps to setting this up. First, we go to the Optical Geometry tab and select an importance edge. In this case, my detector is rectangular, so I'll specify a rectangular scatter area. When I do that, we see that a small rectangular plane has been positioned at the coordinate origin of the system. Now what I need to do is reposition this plane to correspond to the detector position and also adjust the size to correspond to the detector size. I'm going to bring up the triad for that plane and using the mouse, position it just before the detector. Next, I go to the Feature Manager and edit the sketch for that object. Here we set the size of the importance area to be the same as the detector size. The next step is to go back to the Optics Manager to adjust the scattering properties for that surface. Down here it says Scatter Direction. I pull up the list, select Towards Edge, and then over here in the graphic pane, select the appropriate edge. Let's see what the new ray trace looks like. We can see that in this case, nearly all of the rays have reached the detector. However, a few of them have passed around the periphery. That's okay, they will not impact the simulation result. The key point here, however, is that we have traced more rays to the detector per unit time, resulting in better simulation result accuracy. Together, these features allow for more detailed system characterizations, resulting in improved accuracy and efficiency.